All right, so now if you've done, hopefully you've done the master theorem before. Actually, it doesn't matter because I'm going to cover it. Right? So T of n is the time that it takes to multiply two n-bit numbers together. All right? So remember, I have two n-bit numbers and I want to multiply them. It takes that much time. So the question is it n squared or is it faster? Right? So this says how much time does it take to multiply two one-digit numbers together, and it's going to be some constant. Right? And now if I have two n-digit numbers, well, remember I break them into n over 2 digit numbers. Right? And I give two n over 2 digit numbers to my friend, and so it takes my friend this much time to multiply. Right? If it takes me this much time with n digits, it takes my friend this much time with n over 2 digits. Right? But I have 4 friends. Right? And then I personally, I have to add and shift, and that's going to take me some amount of time. Right? Everybody buy that? So this is our recurrence relation. Now, you know that some people, when they teach, they're very anal about details, and some people wave their hands around. Right? So the art is to know when it's okay to wave your hands around. And sometimes you wave them in one way and you get an answer, and then you see, well, was that fair? And you try other things, right? So, we have all these constants k, and I'm going to argue that they don't matter, right? Because we don't care only about the big O of the t, right? If you cared about the actual t, they would matter. But if we don't care about the constant in front, then those k's are only going to affect the constant in front. And maybe you can sort of see that. But you could also claim, by the same argument, maybe the 4 doesn't matter, right? But it turns out the 4 very much matters, all right? And the 2 very much matters. So anyway, given that, we're going to ignore those things. And so I'm always going to say, for my base case, I'm going to write this down. And it's a bit of a lie, because maybe my base case isn't really of size 1, it's size 5, and it doesn't really take time 1, right? But big O, it's good enough. And I'm not going to worry about the constant in front of this, right? But I'm going to worry about those things. Everybody? All right, so now we want to solve this. And if I was trying to solve, right, x squared equals 4, how would I do it? Well, maybe there's some very complicated algorithm that we could learn that would take square roots. But instead, what I'm going to do is I'm going to guess. And I'm going to plug it in and see if it works. Right? So that's what we're going to do here, is we're going to guess. But the t of n is not just one number, it's a function. Right? So we can guess. Here's our guess, G for guess. It's still n squared, but, that's what we got. So you guess it, and you plug it into here and here, and it satisfies it. All right? And so now that tells you that this guess is a solution. Now, just like over here, there could be more than one solution. But it turns out that if you sort of unwind it, you can sort of see that t is determined. Right? So there's only one solution. This is a solution. This must be our unique solution. Right? All right, but the problem with this technique is, how did you come up with that guess? Right? We're not very good guessers. So instead, we're going to try to unwind it. And by picture, I'm going to use a triangle to mean me and all of my friends. And I'm going to use a circle to mean just me. Right? So t of 1 is 1. Now t of n, what's the work of, if I have an input size n, me and all of my friends? Well, it's my personal work, plus I have 4 friends, each have given an input of half the size. Right? Everybody understand how we're just this equation represented in pictures? Right? So sometimes I use these pictures. And so that's that. And then we can unwind them further. right? How much work this guy personally does n over 2 work, because he has an input of size n over 2. And he has 4 friends whose inputs are size n over 4, right? And that unwinds, and it keeps going down until we have the base case, right? So we can try to think about the work at all levels, right? So at the top, up here at the top, there's one of me, and I have an input of size n, right? And then how many friends do I have? Well, I have 4 friends, and they each have 4. I have 4 children, and each of them have 4 children. So I have 16 grandchildren, right? And then I have 64 great-grandchildren, right? And how big are their inputs? Well, my inputs of size n, my children n over 2, my grandchildren n over 4, right? So at the ith level, there are 4 to the I relatives, and each is given an input of size n over 2 to the I, right? So that's the total work at that level. At the base case, the inputs are of size 1, right? So we can calculate how many levels there are. Well, you keep coming down by a factor of 2. They're going to be log n levels, right? So what's true at here? Well, this is going to end up to be 1. That's pretty straightforward. Everybody has an input of size 1. That's how we designed it. But what's this number, right? What's this number? So the way to calculate it is, here we're going to do it in general. What's a to the log n? Well, let's assume our logs are base 2. So then a equals 2 to the log a, right? We're bringing the a up by taking its log. And that's a useful thing to do often in life. If you have a base, you can change the base to a 2 by taking the log of the base and bringing up the log, right? And now we have 2 to the this to the this. What do you do with those thises? Do you add them or multiply them? You multiply them, right? And then now we do it in reverse, right? You bring the log n, and what's 2 to the log n is n, right? So here we brought the a up and we brought the n down. This is n to the log a, right? Everybody understand how we did that? This one, what's 2 to the log n? Right? Everybody buy that? So this is a useful tool, and we're going to do it again, in fact, in a few minutes. But anyway, our bottom line is that our running time, right, that this is the number of base cases. How many base cases do we have along here? It turns out to be into the log 4 base 2. And what's the log of 4? It's 2, right? So the number of base cases is n squared. Right? Well, that was good. Now we need to add up all of this work, right? I personally do order n work, and then it comes to all these levels, and we add it up. Now, how do you add? Well, luckily, I told you that if the terms go up multiplicatively each time, then it's geometric sum, and the sum is dominated by the biggest term, right? So one thing you should know how to do is how to add this up, but the moral is that it's dominated by the biggest term, right? Which you might think is this, right? But if r is a half, then that's the biggest term, right? Then we get 1 and a half and a quarter. All right, right? This is true whenever the terms increase geometrically. All right? That's just showing all the various things. This is showing you my sum equation, right? It says if we're adding up a bunch of things that are geometric, then the sum is the biggest term. Right? or if they're decreasing geometrically, then the sum is big O of 1. All right, so now these terms go up by a factor of 2. Why? Because this is going up by a factor of 4, and this is coming down by a factor of 2, right? And in general, that's going to be this trade-off, right? The number of friends is going to be growing exponentially, and the size of the inputs are going to be decreasing exponentially. And so it depends on which is happening faster, right? And so the sum here is going to be dominated by the biggest term, which is the base cases. Right? Does that make sense? All right, so we had that great algorithm, and it's not any faster. So let's go back and understand the math more. I'm going to give you this chart here. So suppose we have a generic recursive program. In this case, it says hi. So we need to come up with a recurrence relation for it. And how do we do that? Well, we say my input is of size n, right? And then T of n, that is the amount of highs that get printed, right, by everybody. Now, then we can say how many highs get printed by me personally. Right? So these are the highs that get printed. The highs that get printed personally are, right, well, if n is 1, then I print 1 high, right? But for arbitrary n, I print f of n highs, right? So the number of highs I'm personally printing is f of n. And then how many friends do I have, right? This is by all my friends down there. They're printing highs. Well, oh, this is a recursion I gave you, right? This is my personal work. This is how many friends I have, right? So look at, I'm looping here. I have a friends, right? In fact, here, let me tell you something really important about recursive programs. It's a general rule, they're not iterative programs, right? So they don't have loops. Don't think about it as a loop because, you know, there 10% of you, or in the past at least, would give me code that really looks like an iterative algorithm and you get a 0 for it, right? So the only times you're going to have loops is not when you're looping over some iteration. You're looping over how many friends I have, right? Or maybe you could have a little loop in what my personal work is, right? But you're not looping through the algorithm. All right, so what is B? If I have an input of size n and I give my friends inputs of size n over b, which is the case here, right? I'm going to have my input and I cut it up somehow so that this input is a 1/8 the size, then I give my friends inputs 1/8 the size, right? Everybody following that? Yeah? You're all good? You're all bored or you're all lost? Yeah. Yeah. Because I have friends that. So in the iterative example, all right, there's actually an example where my work personally has to do the merging, right? So that part, the merging part, is iterative. But the big picture is not iterative, right? The big picture is I split into two, I give them my friends, and they solve them. That's the end of the algorithm, right? Right, so what's the big structure of the algorithm for an iterative algorithm is one big loop that iterates, right? What's the structure of merge sort? Well, there's this recursive tree, and then each stack frame might have to do the merging, right? I'm going to show you some examples of, well, one example of somebody who gives me really bad code, and you'll see how it's bad. All right, so we put all the pieces together, right? All right, so now we're trying to evaluate this recurrence relation. Remember, this is the work I'm personally doing. I have A friends, and I give my friends inputs that are a beat the size. So A, B, and F of n is always going to be into the C, right? So in the past, I had much more complicated F's of n's, but we're going to let all that go and just let F be into the C. All right? So what are we doing here? What is the size of my input? Well, I have an input of size n. Then my friend's is n over b, right? His friend is n over b squared. Goes down to n over b to the I, right? We're going down by I each time. All right, so when do we bottom out? Do we bottom out when we get inputs of size 0? No, because that's never going to, right? If we do real numbers, that's never going to get 0. So we plug in 1 there, right? And we say, right, we got to calculate what h is going to be. So here, we're solving for this. You bring the b to the h over. You take the log of both sides, which brings the h down. And then you divide by the log b. And what do you get? You get that the height is log n over log b. All right? And so let's pause for a moment, because I just got email from somebody before, just as I was going to bed, who said, well, shouldn't there be a log b somewhere? And I said, well, it depends on whether we're doing big O or not, right? So if we're doing big O, then n's a big number, and so log n's a big number, but the b is a constant, right? So the log b is a constant. And if you're wanting to know what's the height, it's order log n, right? So all of these are going to have height order log n. Why am I including the log b here? Is because sometimes we're going to need more than big O. We're going to need to know what that constant is, right? Remember, and we'll see that in a second, right? We'll see in a second where we need the log b. All right, so that was our instance size. So now, how much work do all of these people do, right? If I have an input of size n, how much work do I personally do? F of n, right? So all of us do f of our input size, right? And then, how many stack frames are there? Well, there's one of me, a of my friends, a squared of my grandchildren, right? So they're a to the I at that level. And how many base cases are there? There's a to the h, right? So now we need to calculate how many base cases there are. And the reason we cared about the log b is because h is in the exponent, right? So that constant matters. So anyway, let's calculate this. And we're going to do the same trick we did before, except I don't have it here. If you really need, I can put it on the board. But basically, the A is going to, right, you plug in H, and you get, what is H? H was log n over log b, right? So the number of base cases is this. And then we bring the A up, and as we bring the A up, it gets logged, right? Remember that? And then we're going to bring the log n down, and as we bring it down, it's going to become an n. People got that? And so what do we get? We get n, which is the number that's growing, and these are all constants, right? N to some constant. It's a polynomial. And what is our constant? Log a over log b. All right? And so really, because why do we get this? Because it's a trade-off between how fast the size is growing, how fast the size is shrinking versus how fast the number of stack frames is growing, this trade-off tells me how many base cases I have, right? And so what do you need to know for your life and for your test is if you want, you can forget all this math. And what you have to remember, this is worth a few marks on the midterm and a few marks on the exam. You need to memorize that the number of base cases is into the log A over log B. All right? So either know how to drive it or know how to memorize it if you want those marks. Right? Everybody got that? All right, so now how much work is done? Well, we take the number of friends at that level times the work each of them does at that level, and we get the total work, right? And then we're going to add that up. All right? Total work is that funny sum, but luckily, usually in most cases, it's either geometrically increasing or geometrically decreasing, right? There's one case where all they're more or less the same, but we'll worry about that case later, right? So now, right, here it's dominated by the first term. Here it's dominated by kind of the last term. So anyway, then, right, what are our two numbers? This number is easy. It's how much work I personally do, right? The running time is at least that. And this is how many base cases there are. And each base case, remember, does a constant amount of work. So the work of the base cases is the number of base cases, which is into the log A over log B, right? And the running time is at least that. And the purpose is to say that the sum, the total running time, is bounded by one of those. All right? So here's our chart, right? So this is the total time of me and all my friends to solve the input of size n, right? What's that? That's how many friends I have, right? What's that? It's the size of my friend's input is coming down by a factor of b. What's that? That's how much work I personally do. And you'll see here I deleted stuff. Remember I told you we're gonna just make this easy and assume that it's into the C. All right? And then, all right, so now the question is, what can we ignore? Right? So what this constant is matters. What this C is matters. Right? The constant in front of this doesn't matter. So let's think about what can be ignored. And suppose you're coming up, the A is pretty concrete. How many friends do I have? Right? But I have my friend's input. I'm saying it comes down by a factor of b. What happens if I round it up? Right? Does that matter? No, it doesn't really matter. Right? In reality, if my friend's input's a little bit bigger, then the time will be a little bit bigger. But does it? Here, I had trouble yesterday. When people ask me yes/no questions, sometimes I have a hard time to know whether I should say yes or no. They say, "Do you mind if I?" Well, you want to say, "No, I do not mind, but yes, you can do it." Right? So anyway, this is it fine? Yes, it's fine to ignore the rounding up. All right? That's fine. What about here? That's similar. I'm adding 1. Right? 1 is just small order compared to the n over b. Right? It's small. What about adding something? What about here? What about this? I'm adding something really quite big. Right? But you know about little o? It's not big O. It's smaller than big O. Right? It's smaller. Right? This is shrinking compared to this. So even that matters, right? But that is a disaster, right? That's way bigger. So that's just the saying, right, how big my friend's input can be. All right, so now, here's the chart when I added in the extra stuff, and we really don't want to go there. we're going to be looking at this case where I subtract a constant from my input, and that's bad. Yep. Well, it's because it turns into an exponential time algorithm. And we'll look at that example later, right? But you can imagine if I have my input and I subtract one of it from it and give it to two friends, what are we getting? We're getting something more like Fibonacci numbers, right, which grow exponentially. Or Tara Hanoi, which grows that exponentially. Yeah? This is our last example, right? Is this what you were? Right. I had my input was 2 x and y with n digits each. I had 4 friends. Each of them were given a and b with n over 2 digits, right? I personally had to add and shift. So this is the running time of that algorithm. Right? Everybody got that? Now, let me show you by example what I want you to do on a test. Right? What you need to do in your life if you have a recursive program. You need to be able to, I'm going to say, what is the running time of your recursive program? And you're going to write down the recurrence relation, and then you're going to solve it. And the way you solve it is you say, how much work is at the top level? Well, it's n to the 1, right? How many base cases are there? It's n to the, you've memorized it by now, log A over log B. You calculate what that is. A's 4, B's 2, log 4 over log 2 turns out to be 2. Now, I'm going to show you in a minute that on the test you're not allowed to have a calculator. So you're going to have to calculate log 4 over log 2 all by yourself. All right? And we'll discuss that in a minute. So, and then you take the exponents of these two. Right? Here the exponent is c, is 1. Log A over log B is 2. 2 is bigger than 1. So we say, hence it's dominated by the base cases, and the answer is order n. Right? Does that make sense? Right? And so now the question is, how are we going to make our multiplication algorithms faster? Right? And the one possibility is to reduce the number of friends from 4 to 3. And so let's see what that does. Does that give us just a savings of 25%? No. Right? So here's our algorithm before. And if we eliminate one friend, we just shot our friend lots of blood. Right? But is that the end? No. All our friends kill off one of their friends. Right? And all of their friends kill off one of their friends. It's just like Game of Thrones. Right? All right, so now we're going to do it again. Now here we're solving the same thing, except we changed the 4 to a 3. Right? So now the number of base cases is log 3 over log 2. Now when I said that you're going to have to calculate this yourself, I somewhat lied because you're not going to calculate this by yourself. Anyway, it turns out to be 1.58 something, right? So then we compare the log A over log B to the 1, the C, and it's still bigger, so it still gets dominated by the base cases, right? But look at the running time is much bigger. I mean, much smaller, right? Big improvement. Everybody got that? All right, while we're on the roll, let's try some more examples. Suppose I personally do n squared work, then everything's the same except C's 2, and 2 is bigger than 1.58, so it's dominated by the top level, right? Clearly, I'm doing n squared work. We're not going to be less than n squared, right? So the running time is n squared, right? Dominated by the top. Everybody got that? All right, so now let's do another funny case. let's say a really weird thing. I happen to spin into the 1.58 time at the top level, right? Then C is 1.58, and log A over log B is 1.58, so they're equal. And what happens is, remember, the tree is always order log n in length. And if all those layers have basically the same time, then the sum is the number of terms times the term. So we bring in an extra log n, and the running time is the work at the top layer and the bottom layer times log n. Right? Maybe I should add an extra slide. Merge sort is in log n. That's where that log n is coming from. All right? So here's all these levels that we have to add up. And if they're all the same, then you get that log n factor. Right? And that's where the email I got in yesterday was saying, well, why don't we bring the log b in here? Right? But now I'm doing big O. And so the log b, we can ignore it. All right, so this is our chart again. This just says we're comparing log A over log B to C. If log A over log B is smaller, it's dominated by the top, and the answer is the work at the top, right? If the answer is the into the 4. And if the log A over log B is bigger, then it's dominated by the number of base cases, right, which you have to calculate what it is, right? And if they happen to be equal, then you get an extra log factor, right? Everybody got that? Yeah. You've seen it before. All right, so here, right, we need to calculate this. And the question is, what base are we using? And remember, I don't often write in the base because I care about the big O in the base. You change the base, just changes the constant, right? So here, how do you change the base to base C is you multiply by a constant, and that constant cancels, right? So it doesn't matter which base we use, so we use the easiest base. And in this case, the easiest base is 3. So you have to know 3 to the 3 is 27, so it's 3. And 3 to the 2 is 9, so you get 2, right? So that you need to be able to do without a calculator, right? And what about this? Do you need to do that without a calculator? Clearly not, right? Everybody got that? I just don't know how to do that without a calculator. All right, everybody good? All right, so now let's go back to our algorithm, right? And we can think, oh, we don't like n-squared algorithms. How can we improve it, right? And can we decrease the n? No, linear time, we're not going to decrease the n. Maybe we could change the 2. In fact, we will change the 2 later. But right now, we're going to change the 4, right, to a 3. And how are we going to do that? Anybody remember? How do we change from 4 friends to 3 friends? Yeah, we kill them. But how are we going to do it mathematically? Remember a technique we talked about? Nobody remembers Gauss? You forgot Gauss already? Right? Let's talk about Gauss. Remember Gauss here? Here I have these 4 numbers as input, and what is my goal is? I don't actually need to compute 4 numbers. I actually need to compute 3 numbers, right? And I want to compute the 3 numbers not with 4 multiplications, but with 3 multiplications. And so how do we do it? Well, we need those 2 terms, so we calculate them. And then we do a weird thing. This is the high and low order bits of x. We add them. High and low order bits of y, we add them. And then we multiply. That's the one multiplication, right? Algebraically, those are our terms, right? right? But we already have this and this, so we can subtract them off. And that leaves us this, which is what we want. Right? Everybody good with that? So that's our algorithm. And so here what are we doing is we break x and y as we did before, right? We did this as we did before. The new thing is that we personally add those, and get a friend to multiply for us. And then we subtract off this bit and this bit, and that gives us our middle term, right? And so that changed the 4 to a 3. Right? Everybody follow that? Which is better. All right? So now, this algorithm is not a practical algorithm. It gets kind of hairy. But I'm going to just do it in order to give you some intuition as to why n log n might be the right answer. All right? So in practice, if you have really big integers that you want to multiply, the fastest algorithm takes those integers, views them as polynomials over a finite field, over complex numbers, does fast Fourier transforms to convert those into sine waves and cosines. Then, instead of multiplying, you can add, and then it converts it back. All right, so we're not going to cover that, but it's cool. All right, so here what we're going to do is let's, instead of breaking them into 2 pieces, break it into d pieces. All right? And so then x is the sum. It's just like we think about these as being our characters, base, right, 2 to the 1 over d or something, and our y. And then when we multiply, we have all these terms, right? So how many friends do we have, right? For every of these and every of these, we have to have a friend, right? So how many friends do we have? D. There's D here, D here. How many friends do I have? D squared, right? So now let's try to solve our recurrence relation, where each friend is given 1 d, and I have d squared friends. Right? Everybody got a recurrence relation? And I'm personally still doing linear. So the top level work is still 1. The number of base cases, right, is log of d squared divided by log of d. Right? Anybody know what the log of d squared is? The 2 comes down, right? So it's 2 times the log of d. The log of d's cancel, and you get d n squared, right? So actually, let me tell you some general thing in life is if I have a certain amount of work to do, and I cut that work up, I partition that work, and I give some of that work to my friends, does work get destroyed? No, it's the same work. It's going to be the same time. It just depends on who's doing it, right? So that's what's happening here. The only way you can save time is somehow you have to kill work, right? Somewhere there needs to be a savings. And here there's no savings, right? So that was no good, right? So what do we do instead? Well, what we observe is that we don't actually need these d squared numbers, right? Remember, because they're just like before, some of the terms get added and shifted. So what you need is for every red bar, you need the sum of the diagonal, right? So the question, now the Gaussian question, is given these numbers and these numbers, how do I calculate the sum of the red bars? And how many red bars are there? There's So somehow we're going to do it where the number of multiplications is equal to the number of numbers that we need to produce, right? Which in this case is 2d plus 1. And that Gaussian trick is way trickier than we're going to do here. But actually, the truth is it goes back to Fourier transforms. So it all boils down to Fourier transforms. But anyway, right, some fancy Gaussian trick. Let's just imagine that we only had this many friends, right? Now we try to solve this, right? Now we want to see, well, what's the log of this? The minus 1 really doesn't matter, right? What's the log of 2d? It's log d plus 1, right? Remember, times turns into addition, right? So so that turns into a plus 1. And again, as d grows, this matters less and less, right? So if we bring up d to be something like log n, then this goes to 1, right? And so then, right, what's our running time? Well, now c and log a over log b are both 1, right? So what do you do when they're the same? You bring the log in, right? And that's where we get the answer n log n. Does that make sense? And just a day or two ago, I was talking to somebody about p versus np, right, which is the question of can you solve these problems in polynomial time. And somebody famous, I forget who, I think we were talking about I forget who. Somebody who wrote one of the famous books. Still, he believes that maybe you can solve these problems in polynomial time, but the constant in front, right? Here, the things approach 1, so maybe there's some algorithm that approaches a polynomial, but then the constant in front gets so big that it's unwieldy. But anyway, I don't know. So here's something I'm actually confused about. When I personally do I always heard it was n log n. And then when I personally crank out the Fourier transform algorithm, I get n log n log n. So that's what's in my slides. I'm told out there somebody has gotten rid of the log n, but I don't know how to. Actually, my algorithm is n log n log n log n log n. You get more. You get all these. It goes on forever, but we're going to ignore that. All right? So here's our algorithms, right? Kindergarten exponential, grade school quadratic. This Russian guy, right? He did that. And then fast Fourier transforms.